Welcome back. We're going to continue our notes. We're looking at linear modeling and predictions. So our whole goal right now is to look at a data set, and we'd like to find a line that will model the data. And we want to actually find what would be considered the best fit line, and use that line to be able to make predictions within the data. So our learning objective is for a linear relationship, use the least squares regression line to summarize the overall pattern and to make predictions. And here's just some bullet points of things that we will get to. If you want to read through them, pause it, but let's continue. Let's go back to our example. So we've seen this example a few times. So we're looking at this line. So we have the scatter plot again with our driver's age and the maximum distance to read a sign, years and feet. So our explanatory response. And using technology, we'll come back and address this equation later, but we find that the best fit line is represented by this equation, where D equals -3 times A plus 576, or we can look at that as the distance, the maximum distance a driver can read a sign from, equals -3 times the driver's age plus 576. So real quickly, let's go ahead and just graph that and see what that would look like, and just do a rough sketch. If we do a rough sketch, recall that this is the y-intercept and that's the slope. Okay, so I took the liberty, so we could just make a little fit line. Remember the y-intercept 576, and it goes down, and you'll see this kind of match up when we do some points down here. So this part says, using the linear equation above, find the predicted max distance each age can read a sign from. So what do we have to do? Well, here's our equation, and this is our prediction equation. So let's make sure we have that set, that this is our prediction line. And it's given by this equation here. So if we want to find the maximum distance, what do we have to do? We just have to plug in the... You will want your calculator handy. We are going to need it for parts of the lecture today, so make sure to have your calculator out and handy so you can practice with it. So plugging in the age, well, 57 years old, our equation up above says that the maximum distance to be able to read a sign from for a driver equals -3 times the driver's age plus 576. So plugging all that into your calculator, you should get 405 feet. Remember, let's include our units, very important. And go ahead and do the next two. I'm just going to write down the answers, so pause it or make sure that you can get it. So plugging those in, we'll have 93 years old is predicted to be able to read a sign from 297 feet. And an 8-year-old, using our prediction equation, is predicted to be able to read a sign from 552 feet away. Okay? So let's go down and talk about these predictions. So if we look at these predictions, well, let's talk about something real quick while we're here. That we want to talk about what happens within the scope of the data. So if we have a linear equation to describe the pattern of a scatter plot, we can use the line to predict a data point that is not there if it lies within the scope of the data. So over here, what's our minimum data point? So our minimum data point is right over here. That's the farthest one to the left. And this is what? Our farthest one to the right is right over here. And where does that look like it hits? So let's estimate this. Halfway through, right, would be 20, 15, 20, 25. This looks about halfway between 15 and 20, so right around 18. And over here, halfway between here and here, this looks about 75, 80, what do you think? 81, 82 or 83, or right there. It's somewhere in that range. So over here we have 83, and this is what we consider within the scope of the data. So we can say that our predictions, depending on how strong the line fits the data, tells us how how confident we would be in our predictions from here to here. And this is what we'd call interpolation. And then what happens past this? Well, we only have data, right, from 18 to 80 for 18 to 83-year-olds, and we don't know what's going to happen past that, and we don't know what's going to happen before that. So what we have here is that this is within the scope, so this would be interpolation. And then if we move outside the scope, so if we come past this way, so if we're before the first data point or after, this would be considered extrapolation. And depending on how well the data fits the line or the line fits the data, we may be able to extrapolate a little bit, but we have to realize that we don't know what's going to happen past this point. So we want to be very careful when we're extrapolating. So we want to recognize that there tends to be more error in extrapolating. And we're going to cover this right at the bottom of the page, and you can see that on the predictions part. So let's go over that again. Let's come down here, predictions. If we have a linear equation to describe the pattern of a scatter plot, we can use the line to predict a data point that is not there if it is within the scope of the data. So what does that mean? That means it's ranging, right, from the minimum to the maximum. So if it's ranging from the min to the max. And when can we not predict, or when will predictions have a potentially large amount of error? When it's, what, outside the scope of the data. So when we are outside the scope of the data. So what does that mean? That means before the minimum, right? Before the min, or after the max. And this just really depends on how well it fits and how far you want to go out. If we were predicting housing prices, for instance, I might feel a little bit confident making a prediction on my house value next week. But would I be comfortable making a prediction 5 years down the line? No. And that's what we're talking about, depending on how well the data is fitting to our prediction equation. So if we look back up here, remember what was our minimum? Our minimum, we said, was 18-ish, and the maximum we said was 83. So this would be in the scope of the data. This would be interpolation. But what about these two? 93 is past the 83, and 8 is before 18, and these would be extrapolations. Okay, so interpolation, extrapolation. Maybe we should write those down, right? Interpolation, and this would be extrapolation. Let's move on to the next page. So here we're going to look at residuals. So when you hear the word residual, I want you just to think of error. Residual is another word for error. And maybe you've heard residual error as a term. So residual just means error. And the error we're looking at is the distance from the line, this prediction, to the actual data point. So I'm going to label this here. Let's remember that this is our prediction line. So if we're making predictions, then, well, how far off is our prediction from what actually happened? And that would be an error. There's an error in our prediction. It didn't match up exactly. So looking at this scatter plot, we're looking at this is Burger King data, and we'll see this graph a little bit later also. We're going to do some more work on this. And here we're looking at the explanatory variable of protein in grams and the response variable as the total fat in grams. So we're predicting the total fat based on the protein level. So here, if we look, we have a point. Put this in red just to match up with the line, that this is our prediction for this point, but this is what actually happened, and that distance is just called the residual error. So the estimate made from a model is the predicted value. This predicted value, you might see it referred to as y hat. That's just the hat on the y. I'm not kidding, so it's just y hat. And the residual, the distance here, we measure this as saying the observed minus the predicted, or if we prefer, we might say the actual data point, what actually happened, minus what we predicted to happen. And if we're looking at the actual here, this is the actual y value, and this is our predicted value. So we could say that this is y minus y hat. And the order does matter. So think about it this way. If we did y minus y hat, which data point's lower? If we look lower, the y is lower than the y hat, right? I'm sorry, these aren't both data points, the predicted value. So this is y minus y hat, or the actual minus the predicted. So smaller minus larger is going to give us a negative value. So this negative here, this negative residual tells me that what actually happened was below what we predicted, or what we predicted was an overestimate of what actually happened. Now, something I want you to notice is looking at the data, notice how the line goes through the data. Would you say this line is kind of trying to model the data? There's no way for the line to go completely through every data point because it's all scattered. But we want to know, well, is this line the best fit line? Could there be another line we draw that's better? So that's what's going to lead us down to the next topic when we look at these two and say, well, which of these two lines is better? And they might both be decent fits, but which one seems like it's a better representation for where the data is and what it's modeling? Some say this one because these three are really close to here and they're really far from here. These say, well, this is more through the data, right? I mean, we could draw a bunch of lines. So there's an infinite number of lines we could draw to model the data. I mean, if I drew a line here, would I use that to make predictions on this data set? No, because it's not even near where the data's at. So we'd like to have some kind of way, and that's where we're going to analyze residuals. Well, this looks like it's hitting. Maybe if we zoomed in, it may not be. Here we have a residual error. Here we have an error. Here we have an error. This looks slightly below, little error. This is below, error, 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 right? We have error everywhere. And what do you think? We'd like to look at this and say, well, which one has less error? And this gets a little bit harder to tell when we're looking at this, because some is positive, some is negative, and in the end we'd like to look at just a single or a numerical measurement to say which one is better. And that's where we come down to the next part, where what are we going to do? Think back what we did with standard deviation. Back in standard deviation, what did we do? We took all those distances and did what? We squared them. Remember squaring all those values, the x minus x bar, doing the standard deviation, because we wanted to look at average distance. And in a sense, that's what we're looking at here, is looking at the distances away. And we squared them to make them all positive. So we're going to do the same thing here to give us one measurement that we can use to analyze. So if we take these and we build these squares, right? Here to here, this was our residual. We went from here to here. And, well, what does squaring mean? Side times side, right? So if we think about it, that we can look at a square as a representation for squaring a value. And when you, what's a side times a side? When you have a square, remember that gives you the area. So we're going to square all these errors, and this would be a visual representation for that. And this is what will give us what we call the SSE. SSE, and this stands for the sum of the squared errors. Sum of the squared errors. So when we compare this and we look at the left, we compare the left one had a sum of the squared errors, had an SSE of 57.8, and the one on the right had an SSE of 43.9. So based on the sum of the squared errors, which one would be a better fit? Well, the right one, right? Because the right one has less error. I mean, if we want to make predictions, I would rather have less error in predictions, so the one that has a smaller error or smaller SSE would represent a better fit. So the right one fits better because it has a smaller SSE than this one. But is it the best fit? It could be, I don't know, right? There's a lot of different lines we could draw. I might be able to find another line that had a lower SSE, and that would be a better fit than this one. But could it be the best fit? It could be. I don't know. All I know is that it's the better of these two. So there is a way to actually find the absolute best fit line that will have the lowest possible SSE. And you're going to hear this referred to as the least squares regression line. Because, well, what do we do here? This is the sum of the squared errors. And the least sum of the squared errors, or the least squares regression line, would be the lowest possible would be the line that has the lowest possible SSE, hence the least part. If it's the least, you can't find anything lower than that. Okay? So a couple ways we can find the line. We would like lines, right? We have some different ways we can find lines. Well, this is our most popular one. We do like our y equals mx plus b, right? That's our comfort, right? We like to see this. This is normally what we're used to seeing, but I want you to get used to not having it always in that order. Most computer programs are not going to output things in this form. They're going to output them in this form. Y equals b plus mx. They actually start with the y-intercept plus the slope times the explanatory variable. And different programs do different things. You might see this as a plus bx. You might see this as y equals b naught plus b1 times x. So different programs give different things. So this is just reversing it. This is how the OLI will look at it. This is how Minitab will output it. You know, the calculator will do different things. So depending on what program you're using, it'll give a different output. But what's the key point, right? The number that's attached to the x, right, or the explanatory variable, is our slope. And the variable standing alone is our y-intercept. So for the equation of a line, remember two things make up the equation, right? We have the slope and the y-intercept. So to find these, we would need the descriptive statistics from, I'm using Minitab in this case, but you might use a different program, Minitab, and then we can calculate slope and the y-intercept. And these are formulas to find the slope and the y-intercept of the best possible fit line. And, well, let's go through this. What is m? M equals, I might put this in parentheses, or you might put the r on top. That's fine. So, do you recall what r stands for? R stands for, this was our correlation coefficient. And what do you think S sub y would mean? This would be this is back from earlier, this is the standard deviation of our y values, standard deviation of the y's. and this would be the standard deviation of the x's. Standard deviation of the x's. So just like before, first thing we needed to find the slope, and then we can find our next point. So what are we doing with our m? We're going to take this and have to plug it back into here, right? So we'll plug it into this equation for m. And let's go back again, and this is our y-intercept equals y bar. This would be the mean of the y's. And then we have x bar, and this is the mean of the x's. Now, let's go back again. Remember, slope is rise over run, and what do we have here? Standard deviation of y over standard deviation of x. Remember, rise over run, or y over x, and standard deviation is the average distance the y values are from the mean of y. And over here we have the mean of the y's, and this is the average distance the data points where the x's are from the mean of the x's. And what do we know? We have the mean of x's over here. So they're still linked and they still work with each other. So let's apply this. Pause it if you need to make sure to get this written down. And let's move on to the example below on how we can use this to find the least squares regression line, or the best fit line. So from the example, find the least squares regression line. So we have the descriptive statistics printed out, driver age in years, maximum distance to read a sign from. This should be in feet. I didn't get that on there. So we have all these statistics, and we need to pick out what we need. So refer back to the top. Remember, there's a couple things we need. What do we need? We need R. We're going to need the standard deviation of the y's. We're going to need the standard deviation of the x's. We're going to need the mean of the y's and the mean of the x's. Well, first thing, what's our R value? R value is our correlation coefficient, and that's the same way of saying the Pearson correlation of age and distance. So this is our R value here, negative 0.793. And then we need to look here and say, well, what's our standard deviation of y and standard deviation of x's? Well, our age is our explanatory, our distance is our response variable, and here's our standard deviations in red. So the standard deviation of y, just make sure you're labeling correctly. The y one is 82.8. And the standard deviation of x is the 21.78. And the mean of the y's, here's our means. Same thing, just make sure to pick them out appropriately. The mean is 423 for the y's, and the mean age, the x's, was 51. And after that, it's all just plug in to get those values. Make a little room down here. So first thing, we need our m equals, and this is where you're going to want your calculator, make sure you can get this plugged in and get these values, is r times the standard deviation of y over standard deviation of x equals standard deviation of y. So we have r first, which is negative 0.793, times standard deviation of y is 82.8 over standard deviation of x is 21.78. Plugging all that in or taking some steps, you should get approximately negative 3.015. We have our slope. Now what? We need our y-intercept. Our y-intercept from above says that it's y bar minus m x bar. And what's the mean? The mean of the y's was 423 minus the slope that we just found was negative 3.015 times the mean of the x's is 51. Plugging all those in, Remember, minus a negative will turn into a plus here, and we will get 576.765. Now we have our slope and our y-intercept. Putting those together, this would give us y equals negative 3.015x plus 576.765. And from our data above, the y value, y represents our distance. Distance equals negative 3.015 times x is the driver's age plus 576.765. And notice how that looks pretty close to that equation on the previous page or two, right? Where distance equals negative 3 times age plus 576. So ours is slightly different, most likely from rounding. Okay. Let's move on to the last page of our video, putting this kind of all together. So here we're going to look at some Burger King data. It says use the data. This is data on Burger King burgers, fish, chicken sandwiches, nuggets, and strips. So here we have our Burger King analysis. We're analyzing the protein and total fat. So down here on the X, this is our explanatory variable, is the protein in grams, and our response variable is the total fat in grams. So we're predicting the total fat based on the protein levels. And this data was taken from July 2015 from the Burger King website. So we have our scatter plot, we have our prediction line, or the least squares regression line. I think it's always helpful just to remind ourselves that when we see regression line, this just means prediction line. So that's our prediction line. What's the equation of the prediction line? Well, here at the top of the display we have our equation given. So it tells us that the total fat is equal to 3.798 plus 1.100, or 1.1 times the amount of protein. So this would be our predicted total fat, since this is the prediction line. And the first question says, what is the predicted fat content for a Whopper sandwich that has 31 grams of protein? Well, 31 grams of protein, that's the protein level, so we're just going to substitute that in for protein. So we can say that our predicted total fat is equal to 3.798 plus 1.1 times the 31 grams. Plugging that in, you should get 37.898 grams of fat. So the predicted total fat on a Whopper with 31 grams of protein is 37.898 grams. So down below, next one, it says the actual fat content ends up being 37 grams. What is the residual for the Whopper sandwich, and what does this mean? So remember, residual just means air. So residual air. And just refreshing, residual is equal to the actual minus the predicted, or the observed minus the predicted. Well, we have the actual. It says the actual fat content ends up being 37 grams. So we have that part. Plugging that in, we have 37 grams minus what was the predicted amount? The predicted was what we just calculated up above. That's 37.898 grams. Subtracting these values, we get negative 0.898 grams of fat. So what does this tell us? Well, we can see by the numbers, right, that what actually happened was below what we predicted. So this tells us that the actual fat content of the Whopper had 0.898 grams less fat than was predicted. So the negative value tells you what actually happened. The actual fat content of the Whopper had this many grams less fat than was predicted, or we can say that our prediction was an overestimate of what actually happened. Which is pretty close, right? If you think about it, that was less than a gram. So our prediction in this case seemed like it was actually pretty good. We were less than a gram away from the predicted value. So just because this seems small, just keep it in mind in the perspective of what's happening with the data, that whether or not that's small or large. But I would say that's a pretty good prediction. We weren't off by very much. Let's continue down and let's look at the slope and y-intercept, and let's interpret those values. I'm going to start by rewriting the equation just so we have a reference on what we're looking at. So here we had the total fat is equal to 3.798 plus 1.1 times the protein. So remember which one is the slope, which one is the y-intercept. Remember, the slope is always the one multiplying, right, with the explanatory. So this would tell us that this is our slope. The slope is 1.1. And this is our y-intercept, 3.798. It's by itself. And before we jump further into here, I want to write a couple coordinates. What does x represent? Remember, read it off your graph. The x-axis is labeled, it says protein, so I'm going to say grams of protein. And the y-axis, the response variable, is the grams of fat. And this will be a good reference when we're actually trying to get our units and interpretations for both the slope and y-intercept. So here we have our slope. We just said the slope was 1.1, but I want to make sure we get the units on it. So is it the x over the y or the y over the x? We know that it's the response y over the explanatory x. In this case, we're going to say grams of fat per gram of protein. So that would be the slope with the units. And now we need to write a sentence to interpret this. So I'm going to write this another way. I'm going to rewrite this and put 1.1 over 1. And then just keep the units where they are. This is 1 gram of protein on the bottom. And on the top we had grams of fat. So read it from the bottom to the top. This tells us that for every 1 gram increase in protein, the predicted fat content increases, right? It increases because it's positive. So we can say for every 1 gram increase in the protein level, or in the protein of a BK entree, what happens? For every 1 gram increase in the protein of a BK entree, the predicted fat content of the entree item, or of the entree, increases on average by 1.1 grams. So for every gram increase in the protein of a BK entree, the predicted fat content of the entree increases on average by 1.1 grams. So remember, put it over 1 and read it from the bottom to the top. For every 1 of this, what happens to the predicted? The predicted either goes up or down by the top item. So remember to use that predicted. These are predictions. Okay, the y-intercept we said was 3.798. So writing this as a coordinate, that would give us 0, 3.798. And, well, let's relate that back up to here. Remember, the x was the grams of protein and y was the grams of fat. So this says that 0 grams of protein will have what? 3.798 grams of fat. So we could say that a BK entree with 0 grams of protein is predicted to have 3.798 grams of total fat, or just say fat. So it may sound a little weird, right? An entree with only 0 grams of protein? That seems pretty unlikely to have that happen, which is true, but let's look up at the data above. Let's go back to our data real quick and take a look at that. Well, what's the minimum value? Minimum data point looks like it's here. Looking at that scaling, that looks, what, maybe around 8? Looks like 8 grams of protein would be the minimum, so 0 would be outside the scope of the data, which makes this an extrapolation. And remember, oftentimes, the y-intercept may be an extrapolation or will be an extrapolation. So it's not uncommon for it not to make sense to actually happen, but this is what the interpretation is. And you'll see negatives on here sometime, and then that even seems more weird because now we have a negative value. So if this was negative, we'd have 0 grams of protein is predicted to have a negative amount of fat. That doesn't make any sense, and that's usually because it's an extrapolation. Okay, hope you've enjoyed the video. I'll see you back for more.